All right, that was just really weird. The recording paused and then started all at once. Anyway, so you're probably like, whatever. Well, let me give you a real world. This isn't even a mathy thing. This is a real world use of this. I don't know if anybody's ever had this happen to them. I have not, but I do know people who have. I don't know if you've ever gotten a speeding ticket from like an airplane. If you've ever been driving out on some freeways, highways, you'll see they have signs that say, warning, speed being checked by aircraft. And what they do is they actually have somebody up in a plane or helicopter or whatever spotter, and they watch cars drive by. The next time you're on the freeway or something, especially if you're out kind of in the middle of nowhere, you'll see these a lot more than like in a city. On the side of the road, like painted on the road, are symbols every like regular distance. Some places are actually painted like airplanes. Sometimes they're just like little arrows or things like that. But they're usually like a mile apart. And here's how they'll actually get you a speeding ticket. So the person up in the plane will be watching. They radio down to an officer who's in a car on the road, and they'll say, "Hey, watch out for the red Miata because it was going 85 miles an hour." And then they go and pull them over. Now, they don't have radar up there. Even if they did, it wouldn't work because they're not like radar works when something's in line with you and not when you're going down. But here's what they do: they use a stopwatch. They watch you pass the marker, and then the next one later they hit stop, and they figure out how fast you are going on average between point A and point B. They found this, the slope of the secant line. And then they radio down and they go, okay, well, between these two markers, this person was going 85, so write them a ticket for 85. And they know that at some point you were going 85 miles an hour because of the mean value theorem. They know somewhere on that interval you had exactly the same speed. It could have been you were going 85 the entire time. It could have been for a while you were going under 85. That means at some other point you were going over 85. They won't necessarily know what that is, but they know for sure, at least it was that average. So they're using the mean value theorem when they time you like that. And that's one that you're never going to be able to argue against. The math just doesn't back it up. Anyway, so there's a like real life place where we use the mean value theorem. Now for us in calculus, and we don't care about speeding cars. And so this also gives us some nice things. And let me show you probably the most important of the consequences of the mean value theorem. There are a bunch, but this one is the one that I wanted to show you. Okay, so this is what we call a corollary. And I don't know if I've ever shown you a corollary. So let me just tell you, a corollary, this is something that comes directly from another theorem. So it's like not special enough, not different enough to be called a theorem itself, but it's a corollary to another theorem. Okay, so this is a corollary to the mean value theorem, but this is big. So this says if f prime of x is greater than 0 for all x in some interval AB, then f of x is increasing. On the interval. And I'll even put not just increasing, how about I'll put always increasing, because that seems a little bit stronger, more forceful. Not just increase, it's always increasing. Now, we've kind of hinted at this when we talked about positive and negative derivatives, how if there's a positive rate of change, like go back to like related rates, right? If there's a positive rate of change, we're talking about, oh, it's getting bigger, increasing. If it was a negative rate of change, it was getting smaller, decreasing, right? So we've kind of hinted at that. But now it's the mean value theorem that guarantees that. Okay, so here's, just think about this. So we're saying that the derivative is always positive. Let's think about if it were decreasing. Okay, so let's say we've got a function that decreases somewhere. So we're going to go from point A to point B. So think about what the mean value theorem tells us. The mean value theorem tells us that there's going to be some point in here, let's just call it C, where we're going to get a tangent line that's parallel to the secant line. So if we're ever at a place where we're going down, that means somewhere the derivative is going to be negative. Well, but I'm being told that the derivative is always positive, which basically means this can't happen. If the derivative is always positive, we can't have this picture that I just drew. Okay, so if the derivative is greater than 0, it can't be decreasing. Okay, well, if it can't be decreasing, then it's always increasing. So that's why this is called a corollary, because it's not like we actually had to prove anything different. It's just, well, it's just sort of a consequence of the mean value theorem.
Is this the same?
Go ahead,
Is
Alia.
this the same, like if the slope is positive, the slope is positive? Like, yeah, it seems too simple. I'm not sure I'm understanding it.
No, you definitely are understanding it. And the fact that you said it seems too simple, no, it is. That's why it's called the corollary, because it's just sort of a, well, yeah, duh, right? But this, what's happening here is we're formalizing, like we are, this is math lawyer. Math lawyer just came out, right? Think about when you're watching, TV or something, and there's an ad about, whatever drug, and the person comes on as a, dramatization didn't really happen or whatever. You get that math lawyer, the lawyerese. This is math lawyer. This is like, yeah, no, yes, you get the idea that positive derivative means increasing. But this math lawyer saying, yeah, but this is why. Here's the paperwork we file with the math judges to confirm what we're saying. So it should sort of feel like well, yeah, of course. Why are we even talking about this? I'm just bringing it up because now we can see why it must be that. I don't know if you're kind of catching what I'm saying here, but this is just, we're formalizing it. We're putting the stamp of approval on what we had said earlier. We never proved it before. It just felt right. But the problem in math is if something feels right, it doesn't mean that it is right. There are lots of times things feel right that are actually not correct. This is saying, you know what? It felt right? Yeah, because it must be. We have verification of it. I don't know if that actually helped you at all, but when your first statement was sort of like, aren't we just saying that, increasing means increasing? Yeah. Right. What we're saying is the idea of a positive derivative does mean increasing.
Okay, thank you.
Yeah, we just checked the box that yes, it must be. So this was if the derivative is greater than 0, but we can also make the argument then if the derivative is less than 0, then it's going to have to be always decreasing. Same kind of argument. Because if at any point we have 2 points where the next one is higher, then we have to have a positive slope, which means we can't be decreasing. All right, so this is the most important corollary because we're going to actually use this now to talk about general functions. And this is what the derivative tells us most about functions. And what we use it for the most is to look at something if it's increasing or decreasing. All right, so let me just kind of write up what all we have here. So a function is increasing if and only if f prime of x is greater than 0. So we're going to be able to tell if a function's increasing by just looking at its derivative, see if it's greater than 0. Similarly, a function is decreasing if and only if f prime of x is equal or is less than 0. And the only other option would be the derivative equals 0. What happens if the derivative is equal to 0? What's going on with a function if its derivative is 0? What kind of function has a derivative of 0? Good, yeah, it's a constant. Thanks, Eric. So if it's equal to 0, it's constant. If the derivative is greater than 0, it's increasing. If it's less than 0, it's decreasing. You already know that for lines, right? Slope, positive slope going up, negative slope going down, 0 slope, constant. Well, this is now formalizing it to any kind of a function. And so on its surface, I mean, it's like, yeah, okay, duh, obviously. But what we're going to want to do is actually look at functions and go, where are they increasing and where are they decreasing? All right, so for example, let's look at f of x equals x to the 4th minus 4x cubed. And what I want to know is on which intervals is f of x increasing and also where is it decreasing? Okay, so that's the question I want to answer. Here is a function. What does it look like? Well, I know a little bit about what it looks like because it's an even polynomial, even degree polynomial with a positive leading term. I know its end behavior is this. It's going to go up on both sides. I know there has to be at least one turnaround point. There could be 3 of them. I don't know if you remember the number of turnaround points in a polynomial could be 1 less than the degree. So that's what I can tell you about it. I could find some points that it goes through by plugging in some x's and all that. But in terms of where is it increasing and decreasing, I don't know. But we can use this. So let's take the derivative and let's look at where that thing is positive and where it's negative. All right, so f prime of x for this guy is 4x cubed minus 12x squared. And what I want to know is when is that greater than 0 and when is that less than 0? So what I'm going to do is actually figure out where it's equal to 0. Because where I can change from positive or negative are on either sides. So I don't know if you remember this from pre-calc, from algebra at some point, But if what you're trying to do is solve an inequality like this, right? So I'm looking at where's this function greater than 0. What the process is to solve it for equal 0, cut the real number line at those places, and then test the intervals that they form. So I'm going to walk you through this one. If after I do this, you're like, whoa, I don't remember this at all, come talk to me in an office hour, and we'll go back and I'll fill in that gap with algebra. But I think after I do a few of these, it'll start coming back. Regardless, let's take 4x cubed minus 12x squared, and let's set it equal to 0. So I can factor out a 4x squared. Gives me an x minus 3. And so from this, I have two possible x's. There's x equals 0 and x equals 3. So I'm going to take the real number line, and I'm going to cut it at 0 and at 3. So think of it just a long piece of string that I literally took scissors and cut. And what I want to do now is test one point in each of those intervals and see what I get. If it's greater than 0, then everything in that interval is greater than 0. If it's less than 0, then everything in there is less than 0. Right? We can just pick one representative. So, for example, pick a number bigger than 3. Let's take 4. 4 is nice and easy. So we look at 4. I'm going to put 4 into f prime. So f prime of 4, if I come right here, 4 cubed is 64 times 4 is 256. This one, I'm going to get 3 times 64, which is 180 something. But whatever that number is, it's a positive number. Okay, so since I get a positive number if I plug in 4, I'm going to get a positive number if I plug in 5, 6, 308, any number bigger than 3, that's going to be positive. All right, well, what that tells me about my function then is that in this interval, my function is increasing. All right, so let's look between 0 and 3. Probably a nice number there is 1. So let's plug in 1. This I can plug in pretty easily. If I plug in 1, I get 4 minus 12, which is negative 8. So I get a negative derivative there. Well, what that tells me then is that my function is decreasing between 0 and 3. All right, lastly, let's plug in like negative 1. So if we plug in negative 1, I'm going to end up with negative 4 minus 12, which is negative 16. So that's also less than 0. So that tells me in here I'm decreasing as well. So we actually know everything about this function in terms of where it's increasing and decreasing. It's increasing from 4 to infinity. Or sorry, not 4 to 3 to infinity. So if we look at the graph of this, from 3 on out, it's going up. And we know that it's decreasing from minus infinity to 0, and also from 0 to 3. Those were the other two intervals that we found. So let me anticipate a question. Why don't we just stick these together? Why don't we just say that it's decreasing from minus infinity to 3? I'm going to guess some of you had that question. Can anybody tell me why?
Because 0 is an x value.
So 0 is an x value, but I mean, so is like 1, which is
I
in
know,
here
but
and all
0 is like equal to 0, and then it's not greater or less than.
Yeah, there you go.
So you
That's
have
exactly
to
what,
put a gap because there's something in the middle that's equal, not less than.
okay. So think about 0 was such that the derivative was equal to 0. And what does that tell you about the function at 0? Well, it's not increasing and it's not decreasing. It flattened out for a second. At that moment in time, the function was not increasing or decreasing. So yeah, from the inequality argument, it's because it's a strictly greater than. From an increasing decreasing argument is, well, it's not increasing or decreasing. At that point, our derivative is 0, so it flattened out. All right, so you can actually now just take any function and figure out where is it increasing or where is it decreasing. So check this out. We can actually draw kind of a rudimentary graph of this function without a calculator, without plugging in points or anything. All right, so here's what I know, what this is going to look like. So here is just on the real number line. Well, let's do actually. Now, what I'm going to draw here, I could be off shifting up or down. But I do know this. I know that it's decreasing until I hit 0. At 0, it flattens out. Then it decreases again until I get to 3, and then it increases. So let me actually even put some tick marks here. So it's going to be decreasing as it comes to 0, but flattening out. Then it's going to decrease again until I get to 3. And then it's going to increase. So here was 3. And you notice that I was decreasing and then increasing. Here, of course, is 0. I was decreasing, decreasing. Again, just remember that this graph could be shifted up and down, whatever. But in general, that's what this thing looks like.
Just to be clear, this is f of x, not f prime of x, right?
That I just drew in blue?
Yeah.
Yes. This is
Okay.
f of x. So x to the 4th minus 4x cubed. And again, remember what we knew. Since it was a polynomial, we knew that it was going to be going up on both ends. Yep. There was going to be at least one turnaround point. Yep. But that's well, it's actually not a terrible graph of what this looks like. Now, we could do a lot more to this to help figure out exactly what it looks like, right? We could find some points like intercepts and all that. But if we just want basic general shape, yeah, it looks like this. I mean, try it out. Actually, I'll try it out. Let me go to my computer. I'll put on Desmos, and we'll draw a graph. We'll see what Desmos says this should look like. All right, so let me share my screen. Let's hit up Desmos. And we're waiting, we're waiting. Okay, there it is. So we had x to the 4th minus 4x cubed. All right, so let me just zoom out a little bit because as it is right here, Can't really see it so well. Let me change the scale a little bit. I'm going to make it so that my x's don't go quite as far. All right, so what do you think? So that's what Desmos says this graph should look like. Look at what we found on the whiteboard. They're pretty close, right? I didn't do too badly. I mean, yes, I don't have specifics in terms of how far it goes down and things like that, but I have the general shape just by looking at the derivative. All right, any questions on this graph from Desmos before I turn it off? All right, cool. So we got a pretty decent feel for what this thing looked like. Way faster than any kind of graphing you ever did in the past. And that's kind of what the point of this is, of what we're talking about right now, is that this is going to give us a really good idea of what these things look like, what these functions look like, without having to go through the torturous plug in x's, get in out y's, connect the dots, hope we find all the important points, blah, blah, blah. We can actually get really, really good detailed graphs quickly. And as we go through the next couple of days, we're going to see other things that we can use other than just the first derivative that will help us make even better pictures. All right, but this was a polynomial, and we already had a pretty good idea of what those look like. So let's answer the same question, but with a different function. And this one, I don't know that you're going to be able to picture what it looks like. But let's look at x plus 1 over x. So exact same question, just a different function. All right, so let's see how this plays out. So what we're going to want to do the same thing as before. Let's take a derivative. Then let's look at that derivative, see where it's positive, where it's negative. Then kind of piece that together. All right, so let's start with f prime. So the derivative of this, well, the derivative of x is 1. 1 over x, its derivative is 1 minus x squared. If I get that as a single fraction, if I just combine it, get a common denominator, it's x squared minus 1 over x squared. All right, so there's the derivative. But now, same question as before is, where is that greater than 0? Where is that less than 0? So again, from pre-calc world, just going to remind you, we're basically looking at this inequality. What is x squared minus 1 over x squared greater than 0? And the process for this inequality is very similar to that of the polynomial. Just when we have a fraction, we need to look at when is the top equal 0 and where is the bottom equal 0. So what we're going to do is we're going to look at both when the top equals 0 and when the bottom equals 0. So it's a slightly different process. But once we have those, we're going to cut the real number line and test again. So this first one gives us plus or minus 1. The second one gives us 0. So we're going to take the real number line and we're going to split it at plus and minus 1 and at 0. So we just created 4 different intervals this time. So we need to test each of them. All right, so we can go ahead and start plugging in numbers. Pick a number bigger than 1, plug it in. Pick a number between 1 and 0, plug it in, and so on. But let me show you kind of a faster way. Look at this fraction. Look at the bottom. The bottom is x squared. That's always positive, right? No matter what, it's going to be positive because when you square a number, it becomes positive. So really, we just have to worry about when is the top positive and when is the bottom, or when is the top positive or when is it negative. Well, think about x squared minus 1. That's going to be positive if x is bigger than 1, right? Plug in 5, plug in 100, right? Anything bigger than 1 will make that positive. So if x is bigger than 1, f prime of x is greater than 0. Plug in a number and you'll see that happen. But the same thing's going to happen if we're less than minus 1, right? Plug in -2, for example. When you square that, it becomes positive and will be bigger than 1. So we actually have the exact same thing happening here. The derivative is going to be greater than 0 when we're down there. Now, between plus and minus 1, when we take that number and we square it, we get something less than 1. So the top of this is negative. And so, in fact, in both of these regions, we get that the derivative is negative. So in terms of increasing and decreasing, it's increasing over here. It's decreasing in these middle two intervals, and then increasing in the last interval. So let's answer this question. So increasing, it's increasing from minus infinity to minus 1, and from 1 to infinity. And then it's decreasing from minus 1 to 0, and also from 0 to 1. Again, I'm not including 0, because 0 doesn't make this a negative number. In fact, 0. Go ahead.
Sorry. I was just going to say, what is the little u between the two parentheses there?
That's a union symbol. That's just what we use when we have more than one interval. So it just means union. And it's what we do when we put two sets together.
Okay.
Just at this point, just go, yeah, that's what we put in there to show that we're sticking them together. It's the glue sticks them together. But like 0, not only does it not make this negative, the derivative is not even defined at 0, right? You try plugging 0 in here, you get division by 0. So derivative doesn't even exist. All right, well, there you go. We just answered the question of where is it increasing and where is it decreasing. Well, let me impress you again by drawing a reasonable graph of this. Okay, well, let me do this first. Let's look at those important points, -1, 0, and 1, and let's look at what they do with the function. So if I plug in -1, I get -1 plus -1, which is -2. So there's a point over here that's -1, -2. When I plug in 1, I get 1 plus 1, which is 2. So there's a point 1, 2. And 0, what do I get if I plug 0 into the original function? I get 0 plus 1 over 0.
Isn't that just 0?
It's not 0.
Undefined.
It's undefined because I'm dividing by 0. Turns out there's an asymptote there. There's a vertical asymptote. So my function's not even defined there, which is why My derivative didn't exist there, right? But 0 is an asymptote. Okay, so I just know that that's what happens at those kind of key points. Now, let's look at what happens in between them. So from minus infinity to minus 1, I have to be increasing. So my function has to be coming up. After I reach this point, I have to be decreasing. Okay, so that means I'm coming up, and then I'm decreasing, but it's going to go towards this asymptote. So it's going to drop towards infinity. If we look on the other side, once I get past 1, it's increasing. Between 0 and 1, it's decreasing, but again, from this asymptote. So what the calculus is telling me is that its shape must look like this. And again, this is f of x. This is not the derivative. This is the original function. This is x plus 1 over x. So all I did, again, notice all I did, is I plugged in these key points just to see what's going on, and then I used what I knew about the derivative. Well, let's see what Desmos says. See if Desmos agrees. So we'll come back over here and switch. Let me share the screen again. Okay, so hopefully you all can see this, but let's change it to what we had before. So we had x plus 1 divided by x. How'd I do? Are you not impressed? Are you not impressed yet?
I'm impressed.
Thank you. I know it's bad. I'm like begging for validation now, right? But I mean, check it out. We knew nothing about this graph other than 2 points and an asymptote. That's all I told you about it. But then the calculus fills in the rest. So this is really, really powerful stuff. If you want to get decent graphs, you don't need graphing technology anymore. All you need is a derivative. But as they say in the infomercials, but wait, there's more. Because we can tell a lot more about these things when we look at some other feature. Anyway, so how are we feeling about this increasing, decreasing business? Terrible? Makes sense? All right, I'm seeing a couple of thumbs up. But before we move on to the next thing, let me just kind of backtrack to something else we talked about. Remember when we were talking about extrema, maxes and mins? And what we were looking for when we looked for extrema, we had to find critical points. Well, this actually lets us test critical points to see whether or not they give us extrema, whether or not we get maxes or mins or neither, right? And so let me just show you this. This is called the first derivative test. And it's the first derivative test for extrema. So here's how this plays out. So first derivative test. Okay, so if C is a critical value for f of x. So remember critical points, right? Critical value. These are ones where either f of c, or sorry, f prime of c equals 0, or f prime of c is undefined, does not exist. Right? Those are the only places where we could have found extremes before, right? So c is this critical value. Then you know f of c is a local max. I'm going to do max first, and then min is a very, very slight variation. But f of c is a local max if the derivative changes from positive to negative at x equals c. So if we go from increasing positive to negative, that gives us a max. And that should make total sense, right? Think about we're climbing a mountain. As we're getting to that top, we're going up. Once we get to that top, we start going down. All right, so if it changes from being positive to negative, that tells us that we actually have a maximum at that point. This is another one that should sort of be like a, yeah, duh. Well, of course. If we're increasing and then decreasing, that means that we're at a maximum. Yeah. So what's it going to change? How's it going to change if it's a local min? What's different here? Or what has to happen with the derivative? Good, Eris, thank you. It goes from negative to positive. Right? So it has to change from negative to positive. We have to be going down and then going up, right? So think of my hand as a min. We're going down here and then up over here. So this is a great way to tell whether or not a critical point gives you a max or a min. It also might not give you anything, right? It's possible that we're increasing and then increasing again. That just means we had a flat spot and started going up. Or decreasing to decreasing, same thing. It's coming down, flattens out, and then decreases. Kind of like the first example I did with the x to the fourth minus 4x cubed. Don't know if you remember that graph. It came down, flattened out, and then went down again. Because there wasn't a change in the derivative. So the only way that you have an extreme value is if there's a change in the derivative on either side, either going from positive to negative or from negative to positive. All right, so that's probably the best way to think about the first derivative test, is just if there's a change in the sign of the derivative, then we've got an extreme. All right, and obviously this is called the first derivative test because we're using the first derivative. It turns out that we will see one called the second derivative test, because you can use the second derivative to tell you if you have a max or a min. But yeah. All right, so that's really what the derivative is used for, increasing and decreasing. Is it getting bigger? Is it getting smaller? This should be really, really comfortable to you because we've been using this idea. Okay, well, the next step then, of course, is to go to what does the second derivative tell us? Now, this is going to be less comfortable because we're not really used to the second derivative so much, but it's very, very useful. So let's go there. What does the second derivative tell us? Right, that's probably what we want to talk about. All right, well, first derivative tells us increasing and decreasing, right? It tells us how the function itself is changing. What the second derivative tells us is what we call concavity. All right, so this tells us the concavity of the function. Okay, so great. What's concavity mean? Well, let's talk about that. So concavity, there are two kinds of concavity. Like, think about this. There are two ways that the function changes. It increases or it decreases. Well, concavity, same thing. There are two types of concavity. We have concave up and concave down. Those are the two types. All right, so a function can either be concave up or it can be concave down. And it can change. It can go from being concave up to concave down, just like a function can go from increasing to decreasing. Okay, but I would say the analogy with the second derivative to the first derivative is first derivative, we are looking for where it's increasing and decreasing. The second derivative is going to tell us where it's going from concave up to concave down. All right, so where are we concave up? Where are we concave down? So concave up, all right, basically what this means is that your shape does something like this. Looks like a smile. Concave down means that your shape is like a frown. Now, you've seen pictures like this, and specifically with the words like smile and frown, happy and sad, you think parabolas. And parabolas are great examples of functions that never change concavity. Okay, so like a happy parabola, it's always concave up. Sad parabola is always concave down. But you can have shapes that change concavity. Let me show you one that we saw not that long ago. So remember this one that was the x to the fourth minus 4x cubed. I want to show you that there are times that it's concave up and there are times that it's concave down. Like in here, you can definitely see concave up. Right? Because it looks like a smile. Same thing over here. Let me make it lessen. We see concave up. However, it also looks concave down for a while. It looks like a frown in here. So here's an example of a function that changes from being concave up to concave down to concave up. Just like you can have a function that goes from increasing to decreasing to increasing and so on. All right, so this is what it means for something to be concave up or concave down. To help you with this, I've got a little mnemonic device. Think concave up like a cup. Okay, it's concave up like a cup. I mean, it even says it there, right? Concave up like a cup. And then it's concave down like a frown. Okay, so if you can put that part of a function on a cup, on a smile, then it's concave up. If that portion of the graph would fit on a frown, it's concave down. Okay, and this is what the second derivative tells us, actually. The second derivative will tell you everything about concavity, whether it's concave up or concave down. So some functions don't even have concavity or have concavity, don't have concavity, like a line. A line doesn't look like a smile or a frown. Never does. So it doesn't have concavity. But most things have at least some kind of concavity because it either looks like a cup or a frown. Another one that we looked at not that long ago. Remember the one that was x plus 1 over x? And so we saw it look like this. All right, well, over here in the negative world, over here, it's concave down. On this other side, concave up. So here's another one that changes from concave down to concave up. Okay, so before we get to how the second derivative tells us about concave up or down, are you okay with the idea of concave up and concave down? Any questions on that? All right, I'm seeing a bunch of thumbs up. Cool. All right, so, all right, this is what we're searching for, but how is it that the second derivative tells us this? All right, well, for concave up, what this means is that the second derivative is positive. And for concave down, the second derivative is negative. So just like the first derivative, positive, negative, told us increasing, decreasing, the second derivative, positive means concave up, negative means concave down. Okay, so why? Why does that mean this? Okay, well, think about being on the smile part. Concave up. Let's look at how the derivative is changing. Because remember, that's what the second derivative is. This is the change in the first derivative. So let's think about how the derivative is changing. So let's come to this smile. And actually, let's go to the bottom first. So right now, the tangent line has a slope of 0. So hold on a second here. So Aaliyah, would y equals 1 over x have concavity or not? Yes, it would have concavity. Let me draw it real quick over here. All right, so there's 1 over x. So does this have concavity? Absolutely. This side is concave down because it would fit on a frown. This would be concave up because it would fit on a cup. You don't have to have the turn back around. If it looks like it would be part of a frown, even just a portion of a frown, it's concave down. If it looks like even just part of a cup, it'd be concave up. Okay, so like even if we were just on, I had just this chunk right here, let's say, from point A to point B, that's still concave up, right? It never turned around, but it fits like it's on a cup. So with 1 over x, it's concave down on the left and concave up on the right. Okay, cool. All right, so let's come back to this idea. Look at the slopes, right? The tangent line. So this tangent line right here has a slope of 0. As I start moving it this way, what happens to that tangent line slope? Is it getting bigger or smaller? All right, so thanks, Bailey. It's increasing, it's getting bigger. The slope is getting larger. So that means the derivative is increasing. Well, if the derivative is increasing, then its derivative must be positive. Well, the derivative of the derivative is the second derivative. Okay, so check this out. This is another consequence of the mean value theorem, right? When we talked about the mean value theorem, positive derivative means function's increasing. Well, that means a positive second derivative means the derivative is increasing. And if the derivative is increasing, we're concave up. Even on this part, the part where it's going down, look at the slopes. The slopes are negative, but they're becoming smaller negative. Well, smaller negative is increasing. They're getting bigger, right? -1 is bigger than -2. So all along here, our slopes are increasing. So our derivative is positive. The second derivative is positive. Similarly, for the one that's concave down, we start with a big slope, gets smaller, goes to 0, goes negative, keeps getting smaller. So the derivative is decreasing. So the second derivative is negative. Okay, so that's why concavity is even a thing. Because these shapes, the frown and the smile, those correspond to increasing derivative and decreasing derivatives, which correspond to second derivatives being positive or negative. Okay, let me give you another way of visualizing concave up and concave down, because for some of you, this whole cup frown thing may not work. Kind of as even with things like, think about when Alia asked about 1/x, right? Because you don't see the cup. Let me give you another way of thinking about it. For concave up, the tangent line is below the curve. And for concave down, the tangent line is above the curve. Let me show you on this kind of like bigger picture, the one that we did of x to the fourth minus 4x cubed. So think about the tangent lines here on the red, right? On the red part. Notice how they're always underneath the curve. And the same thing over here, right? They're under the curve. If you go to the green part, notice that the tangent lines are above the curve. And then there's some point here where it switches, right? So it goes from concave down to concave up. Same thing here on the x plus 1/x. Tangent line is always above the curve on this piece. On the second part, the tangent line is always below the curve. Same thing with 1/x. Over here, the tangent line is always above the curve. On the other side, it's always below the curve. So there's another way to think about concavity is, where is the tangent line? If I were to draw the tangent line, am I going to see it above the curve? Then it's concave down. Is it below the curve? Then it's concave up. And for those of you who are in Tahoe, this is another one that we can relate to a lot. Don't worry, some of you can relate to this too. It's just not your everyday experience. But think about when you're up on the hill on your snowboard, okay, or your skis. If you're in a situation where your snowboard is your tangent line, right? Think about when you're like on a hump. You're going over some sort of a bump. Your snowboard is totally cool. It never digs into the snow or anything, right? Because you're on a concave down surface. If you're on a concave up surface, that's when your snowboard gets, starts digging into the snow. Because your snowboard, that is the tangent line. And on a concave up surface, it's trying to get underneath the curve. Well, it starts digging into the snow. And if you get too much of that, then you face plant. Right? So if you're a skier, snowboarder, you have a concept of concave up and concave down in terms of what it does to you, right? So again, the advantages of living in Tahoe, one of the many, is that you have great calculus examples. To be fair, I can find calculus examples anywhere, but yeah, up in the mountains, we got great ones for things like that. All right, so that's concavity. Now, we're out of time for today, I think. Oh yeah, we're out of time. So what we're gonna do on Friday is continue this discussion. We're gonna look at concavity some more. We'll look at how we can use concavity in addition to increasing and decreasing to get really good graphs and all that. But we also have a quiz. So on Friday, we're going to do quiz. We're going to start with quiz like we always do. This quiz is going to cover sections 4.1 and 4.2. So those are 4.1 is related rates, and 4.2 was the like differential stuff, the linear approximations, the error propagation. So quiz Friday on 4.1 and 4.2. So that will turn on at 8:30 on Canvas. Well, you'll have the usual half hour to do it with the 10 minutes to get it in, whatever. So we'll start class at 9:10. Okay, so Zoom session will start at 9:10. Quiz will open up at 8:30. All right, so you'll do the quiz, then we'll come back. After we do our quick check-in, we'll continue our discussion on concavity and go from there. All right, so that's everything I have. Any other questions for you guys before I stop the recording here? All right, well, hearing none, we'll call it a day.